This is Edexcel 2016 question 5, and it's a kind of mixed, quite long question really, so some fiddly bits as well, things that we see quite often but still fiddly. Part A, one of these kind of questions we're involving histograms where it doesn't get you to draw it, we have to kind of work around things and work out some values. Right, okay, it tells us that the width of this, which is, that's got a class width of 2, and it says, of 1, sorry, obviously, and that's got represented by 1. So clearly, if we've got a class width because it wants to know what the width of the 0.5 would be, we can see that that would be 0.5. For the we're looking at the 3 to 3.5 because the 2 to 3 one had a width of 1. So the width, the class width is 1 centimetre, so 1 centimetre. So a class width of 0.5 centimetre, 0.5 is a width 0.5 of centimetres on the diagram. A bit of waffle, sorry. Anyway, it also says the height of this thing was 4. Let's just draw that actually. We've got the, well, we've got 1 times 4. And that's obviously got an area of 4. But we know that the frequency is 8. And area is proportional to frequency. That's how a histogram works. So in this case we can say, in general, the area equals to half times the frequency. Or frequency is double the area. So we know, because the frequency of this is 17, we know the area of this needs to be half of that, which is 8.5. Okay, so that just leaves the fact that leaves h. So let's say width, just to be clear what we're doing. Width is 0.5. So the area is h times 0.5 is the area, which is 8.5. So h equals 17. Bit fiddly, but I think I see those things quite a lot. They seem to be quite popular a few years ago. It's popped up again. And linear interpolation is also a bit fiddly, but we see a lot as well. Right, okay, so let's get on with that. Okay, so linear interpolation. The normal textbook that people use makes a bit of a meal of linear interpolation, I think. So anyway, I'm just going to do this quite quickly. We've got the median. Well, first of all, we're going to take it as the 50th, even though it's, because not the 50th, the 25th, because we've got 50 in total, so we halve that. So we want the 25th. You can take 25.5 as well. So the 25th. And then we take the 25th, and we can see, looking at the cumulative frequency, we've got 9 up to that group, and we've got 26 up to, not 26, that's 9 plus 17, yes it is 26 in that group. Okay, so we know the median is here somewhere. Okay, and we also kind of have a sense it's quite a long way into this group because we want the 25th, and the 26th is the last one in that group, so we have a sense that it's closer to 3.5. But anyway, it's some number greater than 3. Okay, and then what we do is we add on the proportion it would be, and I'll do a diagram to help us explain why this is, but we've got a class width of 0.5, and we want to see what fraction of the group that this is in. Well, we've got 17, some number out of 17 is what we're going to multiply by. well, we want the 25th, and before the 25th we've got 9, so that's a 25 take away 9, which is equal to 16. So that's going to be our median, which comes to 3.47. Okay, so intuitively I think that's kind of makes sense, but I'll do a diagram for those of you who perhaps struggle with this. Might not help, but we'll do it anyway. 3 to 3.5 is, we know the median is somewhere there. We know that there's 17 that go along that group there. Remember, this is a number line here, 3 to 3.5. Let's take that latitude. And then we want to find the 16th, because basically we've got 9 up to here, and then we've got a further 16 would give us the 25 up to there. So we want the 16th, basically it's equal to the 25 take away the 9 from before, which have occurred before. So we want the 16th in that group. So we have a sense it's close to 3.5, and that's where that for Excel is. And we have to times by 0.5 because that's the class width there. Anyway, that's part B done. Let's have a look at part C. Calculate so that an estimate of the mean of these babies is 3.34 and find a value for the standard deviation. Right, okay. Pretty standard stuff this. Some people might choose to use a mode on their calculator here, but I think it's probably a bit of a waste of time, because by the time you fiddle around with it and put it in, you might as well work it out, because it's told us for the standard deviation what this number is anyway, so it's probably a waste of time to use a mode on your calculator, the stat mode. So we have these numbers multiplied for sigma fx, which is equal to 1 times 1 plus 8 times 2.5 plus 17 times 3.25 plus 17 times 3.75 plus 7 times 4.5, and that equals to 171.5. So the mean is equal to 171.5 divided by the total number of values, which is 50, which is 3.43, and it's a given answer, so we need to make our working clear. Let's just move this down a bit to make a bit of space. Okay, so the second part of that, the standard deviation is going to be equal to the square root of, because remember it's a standard deviation of W we want. It's going to be the square root of some stuff, and it's sigma x squared, which is equal to the number we got here, 611.375, divided by 50, take away this number squared, and put in the exact number rather than the approximated 3.43. So that's, oh no, it might be 3.43 exactly. Yes, it is. So I am going to just use the 3.43 squared there for ease of calculation. But be warned, this is where accuracy errors can, when working out standard deviations, because of the minus here, you can get big inaccuracies for rounded out, and the fact that you're squaring this number. If that were 3.43 a rounded answer, and we say the number were 3.4347 or something, and we use the rounded answer, that's going to make really quite a big difference, because we're taking away the number. Here it's okay because 3.43 is exact anyway. Anyway, that comes to 0.680 to 3 significant figures. Right, okay, so that's part C done. Okay, part D is normal distribution. Looks pretty standard stuff really, no pun intended. We've got P W less than 3, if we're using this model, using the standardized thing, that's what the pun was, what I'm talking about, using the standardizing formula, that's the same as the probability that Z is less than 3 take away the mean divided by the standard deviation. And that equals to the probability that Z is less than minus 0.615. And if we do a diagram for that, it's basically this part of the that we're looking for, minus 0.6115, which is the same as this, where we've got 0.6115. Okay, so that's what we're going to look for in the tables. So that's going to be equal to 1 minus the probability that Z is less than positive 0.6615 by symmetry. And if we look that number up in the tables, now we're not expected to interpolate here, we can go for the closest one, which is 0.7454. Okay, so you don't have to go in between or anything like that when you're using a rounded answer. It'll prove perfectly acceptable. Some people use calculators for this, which is also okay as well. Still not in the habit of doing it myself. So it's 0.7454 from tables. So that's 1 minus 0.7454, which is equal to 0.2546. Okay, and that's the answer to that, or an answer. They accepted any number in the range 0.254 to 0.255. Okay, so part E and F, let's just bring that up. Now part C is one of those things where so long as you justify your answer, you can get the marks here, whether Siam's decision is a good one or not. First of all, I would say the mean is very close to the median. Close to the median. And that's so it's symmetrical approximately. Well, there's not, or it doesn't seem to be a lot of skew. And then we've also got this answer here, the probability that W is less than 3 is 0.2546. Okay, but when we look at the actual data, we've got that is actually 9 out of 50. So compares, or is the model, or probability W less than 3, whereas the actual is equal to 9 out of a total of 50, which is equal to 0.18. Now here's a case of take your pick. But I would say this would suggest to me, and this is just my answer, you could say it's similar and get the answer and say it's a good model, but my answer would be suggest standard deviation is different. Deviation, inaccurate. But that's my answer. So long as you justify it using a comparison, the mean, saying it is kind of means approximately equal to median, so symmetrical. But you can even say, they even allowed, although I don't think it's probably reasonable, to say that these are quite different. I don't think they are. 3.47 and 3.43 are actually quite very similar to me, but they actually accepted people who said it wasn't symmetrical because these aren't the same. So it is a case of just make your judgment, but do the comparison and justify. Okay, inaccurate, so not a good model. That's my answer. an answer. Just justify it, user comparison. Okay, so that's part D. And then finally, I think that was part E. So my apologies, what happened to D? Yeah, this is D, so this is E. Here we go. Right, so we're going to do part F. Sorry for waffling on, I'm trying to rush this off because people have been nagging me to get the solutions before Wednesday's exam. So it now says a newborn baby weighing 3.43 is born at the hospital. Without carrying out any further calculation, state, given a reason, what effect the addition of this newborn baby would have on your estimate. Well, the mean is obviously unchanged, since the baby has mean weight, so the mean has got to be unchanged. You know, we've got a load of people 50 years old, you know, a bunch of with average 50-year-old. You put another one in who's 50, then of course the average remains at 50. So that's pretty straightforward. Second one, the standard deviation obviously decreases. You can't get away with just saying it obviously does. Doesn't though. Standard deviation decreases. Right, why? Well, I think perhaps too often, and I do this when I teach it as well, we skip over why the standard deviation is what it is. We normally use this formula, sigma x squared over n, take away x bar squared or something like that, and just say it's a I do it sometimes if we're in a rush, and we just say it's a measure of spread. But actually, there's a formula, there's a kind of first principles formula, if you like. X minus mu, x bar, I shouldn't really use x bar in this context, but it doesn't matter. So x minus mu squared over n, that's the other formula. So in other words, it's the sum, that's the variance, and it's the square root of that. It's a standard deviation. So the sum of the squares of the deviations is unchanged, but the number has increased. So that's what I would say. Sum of squares of deviation from the mean stays the same, because the extra one is the mean. So, you know, if you add in that extra baby there is 3.43, that one's going to add nothing to the sum of the squares of the deviations. Stays the same, but n increases by 1. And so that's it, because, and that's the answer. So something like that is fine. The mark scheme, looking at it, standard deviation will decrease. Extra value is at centre, so data more concentrated. Yeah, okay. So the extra value, data is more concentrated because you've got one more right in the centre. They would accept that too. But what I've said is fine. It's going to get the marks because it gets the idea across why. But it's referring it back to the original, to the formula, which seldom uses. Occasionally it's used, but in S1 it kind of makes a reappearance a little bit later on in stats modules, but we don't tend to use that. And sometimes, shamefully sometimes, we don't even really teach it. Okay. That's that question. I don't know if I'll have time to do question 3 tonight. I'm going to try, but anyway, hope you found it useful.